Hello and welcome. In this session, we will master the art of designing, building, and troubleshooting continuous data pipelines in Snowflake with a specific focus on tasks. Let's dive in. We begin by defining what a task actually is within the Snowflake ecosystem. Think of a task not just as a scheduled query, but as the fundamental unit of execution for your data pipeline. It wraps a single SQL statement or stored procedure to automate your logic. Next, consider how these tasks wake up. You can set them on a strict schedule using cron syntax, or for continuous pipelines, trigger them only when new data arrives. Finally, you have flexibility in how they run. You can let Snowflake manage the compute resources serverlessly, ideal for variable workloads, or pin them to your own virtual warehouse if you need predictable performance for heavy lifting. This diagram visualizes the basic life cycle of a task. Starting on the left at node A, we have the trigger source, which can be a time-based schedule or a data event. This trigger activates the Snowflake task at node B. From there, the flow moves to node C, where the task determines its compute model. It branches to either node D, using Snowflake's serverless resources for automatic scaling, or node E, using your pre-configured virtual warehouse. Regardless of the path, they converge at node F to execute your defined SQL or stored procedure logic. Why should we build pipelines with tasks? First, they provide native orchestration. You can chain tasks together into a directed acyclic graph or DAG, ensuring steps happen in the correct order without external tools. Second, they are the engine behind change data capture. By pairing a task with a stream, you process only the new or changed rows rather than reprocessing entire tables. This leads to our third point, efficiency. Using the when clause, a task can check if a stream has data before spinning up compute, ensuring you never pay for an empty run. Here we see the efficiency of a task-based pipeline. Data changes occur in the source table at node A, which are captured by the stream at node B. The task acts as the gatekeeper at node C. It checks the stream's status. If there is data, we follow the path to node D, processing only that delta and updating the target table at node F. If no data exists, we take the path to node E, skipping the run entirely and saving compute credits. Designing a pipeline often requires multiple steps. In Snowflake, we structure this as a task graph. Every graph starts with a root task. This is the only task with a schedule. It kicks off the entire workflow. Dependencies are defined simply by creating subsequent child tasks with the after keyword, linking them to their parents. Crucially, for robust pipelines, we design finalizer tasks. These are linked to the root but run last, regardless of success or failure in the graph, making them perfect for releasing resources or sending status notifications. This diagram represents a robust task graph. Node is our root task, the trigger point. Once it finishes, it triggers nodes B and C in parallel, showing how you can branch workflows. Both B and C feed into node D, meaning task 3 waits for both to complete. Finally, connected by a dotted line to the root, we have node E, the finalizer task. It waits for the entire graph flow to conclude before executing its cleanup logic. Now let's look at the build commands. You start by creating a stream on your source table to track inserts, updates, and deletes. Next, you define the task. Notice the critical when clause in the syntax. This calls the system function system$stream has data, linking execution to data availability. Finally, and this is a common gotcha, you must explicitly resume your task. All tasks are created in a suspended state by default to prevent them from running before you are ready. This sequence diagram outlines the setup steps. First, the user sends a request to create a stream. Next, the user creates the task with the conditional logic. The note highlights that the task remains suspended at this stage. The final step is the user sending the alter task resume command, which transitions the state to started, allowing the pipeline to begin processing. When configuring your task, you must choose a compute model. Use serverless when your data volume fluctuates. Snowflake automatically resizes the compute resources for you. You can guide this with the initial warehouse size parameter. Alternatively, use user-managed if you have a dedicated warehouse with predictable usage patterns. Regardless of choice, always implement safety rails. Setting the user task timeout MS parameter ensures that a stuck task doesn't run indefinitely and drain your budget. This decision tree helps select the right compute model. Node asks if the workload is predictable. If yes, proceed to node B for a user-managed warehouse, leading to fixed sizing at node E. If no, proceed to node C for serverless compute, utilizing auto-scaling at node D. Both paths converge at node F, emphasizing the universal need to set timeout safety parameters. Even well-designed pipelines fail. To troubleshoot, your first stop is the task history table function. It provides the exact error code and state for every run. For complex DAGs, the complete task graphs view helps you pinpoint which specific node failed the whole graph. Proactively, you shouldn't wait to check these views. Design your tasks with an error integration. This pushes alerts to your cloud provider's notification service immediately upon failure, allowing for rapid response. This flowchart maps the troubleshooting process. A task failure at node A triggers two parallel paths. Path B checks if notifications are configured. If so, node C confirms an external alert is received. Simultaneously, at node D, you query the task history view. This leads to node E identifying the specific error code. You then proceed to node F to fix the logic, and finally node G to retry the task.